Hello viewers, welcome to CEC Gurukul lectures. In my previous lecture, I had discussed the history of optical isomerism, and we had concluded that a molecule will be optically active if it forms a non-superimposable mirror image of itself. So now the question arises, why are certain compounds optically active? In order to be optically active, a molecule should be chiral. A molecule which is non-superimposable on its mirror image is a chiral image, is a chiral molecule. The term chiral is derived from the key Greek word chir, which means hand. Our left hand and right hands are non-superimposable mirror images of each other. Here we have our left hand and this is our right hand. They are made up of same parts, yet they are non-superimposable. Now supposing I shift this hand slowly towards my left hand and place it on my left hand, what do we find? That these two hands are not superimposable. Let me demonstrate this. This is my left hand and this is my right hand. Both are made up of same parts. But now when I try to superimpose this right hand on my left hand, I cannot do so. Supposing I keep this hand constant and I slowly move my right hand in the same plane, what do we find? That these two molecules are not superimposable. That is, in this case, the thumbs are on the opposite side. Even the orientation of fingers is different. This is the little finger here, this is the little finger here, and even the ring fingers are, this is the ring finger here and this is the ring finger here. So ring fingers are also on the opposite side. So what I am trying to tell you here, that no matter, not only this, even if I try to rotate these two hands like this, again what I find, that they are non-superimposable. So what I am trying to tell you here is that no matter how the two hands may be oriented, never will all the major features of both hands coincide across all the axes. So an object or a system is said to be chiral if it is different from its mirror image, that is, if it is non-superimposable on its mirror image, and such molecules will be optically active. Whereas, now let us look at another structure, which is a flask. And now if we try, again I will move this flask towards the flask on the left hand side in the same plane, what we find, that this flask, when I'm or let me move the left towards the right slowly, what we find, that these flasks are superimposable. They are superimposable. That is, there is an element of symmetry in this flask, and such molecules which can be superimposed, or such articles which can be objects which can be superimposed, will be optically inactive. So the term chirality was first used by Lord Kelvin in 1893. He, during one of his lectures, stated, and I quote, I call my geometrical figure or group of points chiral. That is, we can take our hand and say it is chiral and say that it has chirality if its mirror image in a plane mirror, ideally realized, cannot be brought to coincide with itself. So here we can again just visualize our hands and see that they are non-superimposable on each others. So all such geometrical figures which do not coincide with their mirror images are non-superimposable. So when we talk, before I proceed further to organic molecules, let us consider, is chirality only restricted to organic molecules? But if you look around you, you will find chirality all around you in universe. It is not only objects which will show chirality, many plants, animals, DNA, important biological molecules also exhibit chirality. Plants show chirality in their growth patterns. Some twiners wind around the supporting structures in a left-handed manner, while others wind in a right-handed manner. On your screens, you can see the growth pattern of a climber which is climbing up. So this particular climber is a sinistral climber, that is, it is twining across this wood or across this support from right to left. You can see it is going from right to left when we are considering it the growth from bottom to top of the twiner A. That means, supposing I say this is the support or this is the axis, now this is going from right to left. That is how the twiner is growing. Whereas if we look into stem B, we say it is a dextral climber, since it is twining from left to right. It is twining from left to right, that is in a anti-clockwise direction. That is, again consider this to be the axis, and this is going like this. This is climbing like this in this direction. So we say it is climbing in a left to right direction, or it is climbing in a anti-clockwise direction. But by this view is perspective is relative, because if you will view this same twiner from top, its pattern of twining will be opposite. So it will depend on the perspective from where we view the growth of these twiners on this support. You will be the beautiful snails which we see, even their shells show different two coiling patterns. That is, the coiling pattern can be dextral, that is right-handed, or it can be sinistral, which is left-handed. I have taken this beautiful picture and tried to show it to you here on your screen. So the photographer did a marvelous job in clicking this photo. That is, he took the shadow of this snail in water, and now what we can see here as the snail and its reflection in the mirror. So what we find here, that here the growth of the rings or the coiling is anti-clockwise. In this case here it is going from here, whereas when we look into the mirror image or when we look into the reflection of this snail in water, what we find that this coiling is in the clock hand direction. So these two are the mirror, the snail and its reflection in water are mirror images of each other, and we find chirality in the growth pattern here also. You will be surprised to know, doctors would of course be knowing this, that human anatomy is naturally chiral, with the heart, stomach and spleen on the left hand side and liver and gallbladder on the right hand side. When we are looking at our body from outside, we do not realize that our anatomy is chiral. That is, we have our heart and spleen and stomach on the left hand side and liver and gallbladder on the right hand side. DNA, the molecule of life, is also chiral. That is, it is, and the DNA which is occurring in nature is dextrorotatory. So what do we say? And we will find only one type of DNA in nature. That is, nature is highly stereoselective in manufacturing or preparing compounds. Whereas when we will prepare this DNA in laboratory, we can prepare both the components, both the molecules, that is the D form as well as the L form. The beauty of nature is that it is synthesizing only that molecule which is biologically active. That is, this DNA is responsible for the life in organisms. So now if we go on to leaving the biological world behind, now let us come to the materialistic words, or to the word of our language, and there we find that some English alphabets also show chirality. That is, if I look into the structure of Q, P or R, these do not overlap. That is, when I say these do not overlap, what we mean here is, that is, we are moving this molecule in the same plane towards this, and they will not superimpose each other, they will not overlap. And then what we can do is, we can even rotate this molecule, and when we rotate this molecule, we find that these two P's are on the head are on the opposite side. Similar cases in the we can find for R, and similar we can find for Q. So these alphabets are also chiral in nature. So from this we can now conclude that all asymmetric molecules are chiral. That is, here we have tried to cut this, we have cut this molecule, this our hand. I started with the concept of chirality with the hand, and this is where I'll continue from there, or this is where I will end this part of the chirality, that when we divide this molecule in this hand into two halves, we find that these two halves are unequal. So this our hand is asymmetric in nature and will not superimpose on its mirror image. Whereas if it was a chiral substance, it was a symmetrical substance like ball or a glass, then those molecules, those substances, those objects would be achiral, because they will be superimposable on their mirror images. Now let me carry my discussion further by taking a simple example of methane, and I will try to explain here how we come to a chiral molecule, or how we get which molecule is chiral in nature. So if I look into the simplest structure, which is of methane, and which you can see on your screens, what we find that this carbon is attached to 4 hydrogens. So before proceeding further, I had explained this before also, but here I have taken a 2-dimensional representation of a 3-dimensional molecule, that is of a tetrahedral structure, and we say that these bonds are representing the bonds, these lines are representing the bonds which are in the plane of the paper. This bond, which I have shown by a broken wedge, represents that this is representing the bond which is going away from us, and it is in the plane of the paper. It is going back. Whereas when we talk of the wedge, then wedge is this bond represents a bond. This wedge represents a bond which is coming out of the paper towards us, whereas this was representing which is going in the paper away from us. So what we find when we look at the structure of methane, we find that these two structures, that the this methane and its mirror image, both are superimposable on each other. And since they are superimposable on each other, they are not optically active. Now let me take another example in which we have replaced one hydrogen of methane with fluorine. And now if we try to pull this molecule on the original molecule, we find they are again superimposable because they are still symmetrical. That is, this carbon is still attached to 3 hydrogens. So this is here we have the symmetry in the molecule, and they will be superimposable. Now let us see what will happen if we replace 2 hydrogens with 2 fluorine atoms. That is, we will get difluoromethane. And when we look at this difluoromethane, we find it is less symmetrical than fluoromethane as well as methane, but still there is little symmetry in the molecule. And when we when we put this molecule on this, we will find that these 2 molecules are superimposable. That is, this fluorine will come on this fluorine, this fluorine will coincide with this, and these hydrogens will coincide also. So we say that this molecule has a plane of symmetry through HCH bond. That is, if we cut it from here, H will be superimposable on H, F will be superimposable on F here. And this will also has a plane of symmetry through FCF bond. So this molecule is symmetrical. Now let us see, again we are taking a disubstituted product, which is fluorochloromethane. But now here we have 3 types of atoms in the molecule. Even when we have 3 types of atoms in the molecule, this molecule is still superimposable. These 2 molecules are superimposable. That is, one is mirror. These are superimposable. That means that why are they superimposable? Because we find that there is a plane of symmetry through Cl, C and F bond. That is, these 2 hydrogens will coincide with the hydrogens in this molecule. So we say that in spite of having 3 different groups, this molecule is optically inactive because they are symmetrical at one point. So now let us represent this molecule in ball and stick model, And what we find in ball and stick model, supposing this is the carbon which is attached to two hydrogens, that is, if let us imagine that this is the molecule of fluorochloromethane, and these two hydrogens are same, and supposing this is fluorine and this is chlorine, so these are different. Now you visualize that we are dividing this molecule into two equal halves, that is, this is the first plane, and when we cut this molecule through this plane, we find that these two hydrogens here are superimposable. Or when we look at the mirror image of this molecule will be superimposable. So this molecule has an element of symmetry, that is, it is symmetrical, that is, it has a plane of symmetry which is dividing the molecule into two equal halves, so that one half is superimposable on the other. That means now this molecule will be superimposable on its mirror image and will not be optically active. So here again I have taken an example of chlorobromomethane, and when we look at the structure of chlorobromomethane, we find they are mirror images of each other. But now the question arises, are these images superimposable or non-superimposable? So to find out this, we can either directly relate these two images to each other, or what we can do is we can rotate one of the molecules in such a way that these bonds align with each other. If on rotating these bonds are aligning with each other, as you can see here, that hydrogens are aligning with hydrogens, chlorines are aligning with chlorines, and bromines are aligning. So that means again this molecule is achiral because it is both the molecules are mirror images of each other. That means the mirror image of bromochloromethane is superimposable on its original molecule. So we say they are optically not active. Now let us go on to next example, in which we are replacing all the four hydrogens by four different groups, that is bromo, chloro, fluoromethane. Now this molecule will have no plane of symmetry. Why will it have no plane of symmetry? Because in this molecule the central carbon atom is attached to four different groups, that is carbon is attached to H, bromine, chlorine and fluorine. And this is what Van 't Hoff had predicted in his experiments, that if the molecule has tetrahedral structure and the four groups attached to the central carbon are different, then those molecules will form non-superimposable mirror images of each other and they will be chiral. This is what we find here. So that means now no matter how we rotate these molecules, we will find that all the four groups are not coinciding here. Here we can say that hydrogen is coinciding with hydrogen, this group is coinciding, but these two groups are not coinciding, they are different. So we say that this molecule, that is, are non-superimposable mirror images of each other and each molecule is optically active. So now the question arises, what is the cause of chirality? A molecule will be chiral if it has an asymmetric carbon, that is a carbon which is attached to four different groups, or this asymmetric carbon is also known as stereogenic carbon because it is the presence of this stereogenic carbon and the orientation of these 4 groups around this stereogenic carbon, which will give rise to the stereochemistry or stereoisomerism of this molecule. That is, this molecule will show optical activity. So this carbon here is the stereo center, or it is the stereogenic center, and we call it as a stereogenic center since this carbon is responsible for the chirality of this molecule. So when we will call this molecule, we will say this molecule is chiral. Now why is this molecule chiral? This molecule is chiral because it has a stereogenic center or a stereo center, that is center which is attached to 4 different groups, and as a result of this, now this molecule is asymmetric in nature. So the molecules will be optically active if they are asymmetric and they have only 1 chiral carbon in them. If supposing the molecule is having 2 or 3 chiral carbons in them, then in that case we will say that molecule will be optically active if the molecule is dissymmetric. For this we shall be discussing the elements of symmetry in my next lecture. So this molecule is optically active because it has a chiral carbon, and what we find that the molecules, and we know that this molecule will be non-superimposable on its mirror image. So we say molecules which are non-superimposable mirror images of each other are called enantiomers, and enantiomers will always exist in pairs, that is, one will be dextrorotatory and the other will be levorotatory. And enantiomers is derived from a Greek word where enantio means opposite, meros means parts. So that means enantiomers are molecules which have same molecular formula, same structural formula, but the orientation of groups in space is different, and this orientation is giving rise to optical isomerism. Not only this, now we know that the pair of enantiomers will have same physical and chemical properties, but they will differ in their behavior towards plane polarized light. That is, one of the enantiomer will be dextrorotatory and the other one will be levorotatory. Therefore, we conclude that optical isomers are the compounds or the molecules which will exhibit the phenomena of optical isomerism. So this phenomena, that is in the direction, the way in which they rotate the path of plane polarized light, is known as optical isomerism. And we find that these two structures are identical but differ from each other by having different arrangement of atoms in groups in space. So from here we will conclude that is the angle of direction is different, that is a molecule is dextrorotatory or levorotatory will depend on the orientation of groups in the space. That is, if the since the orientation is different but the groups are same, the direction of rotation will be different but the angle of rotation will be same. That is, the angle of rotation is same because the groups are same, but the direction of rotation is different since the groups are arranged differently in space, so they will interact differently with plane polarized light. Before I conclude my lecture, let us see a simple mechanism of enzymes. We say certain enzymes are able to work on proteins which are known as peptases. These peptases cannot work on carbohydrates. Why is it so? Because the configuration of the substrate is different. That is, configuration of my proteins that will be different as compared to configuration of a particular carbohydrate. So this is imagined like a lock and a key. That is, if we have lock and a key and we try to fix the key of one lock into the other lock, it will not open it. Similarly, all biological molecules have specific activity. That is, one molecule will work on one class of compounds, one enzyme will work. Supposing when I refer to a molecule, I refer to an enzyme. That is, one enzyme is working with one substrate. It will not work with the other substrate. Imagine, substrate is the lock and enzyme is the key. So it will not fit into different substrates. So I conclude by saying that optical isomerism will be shown by those compounds which are chiral in nature, that is, they have an asymmetric carbon and they are non-superimposable mirror images of each other. Thank you.